So today we're going to go over the mapping lab. So the first thing that we need to go over is latitude and longitude. So latitude and longitude creates a coordinate system for locating precise locations on Earth, and it uses degrees of latitude and longitude. The main lines of latitude and longitude are the equator and the prime meridian. The equator is the 0-degree line of latitude, and it runs from east to west along the widest part of the Earth. It divides the Earth into the northern and southern hemispheres. The prime meridian is the 0 degrees longitude, and it runs from north to south. It passes through Greenwich, England, and it divides the Earth into the western and eastern hemispheres. On the other side of the Earth, the line is called the international date line. So this is a grid showing latitude and longitude. And note where the equator is. It's this blue line going horizontal across where it says 0 degrees. And the prime meridian is the 0 degrees going vertically. Everything to the left of the prime meridian is the western hemisphere. Everything to the east of the prime meridian is the eastern hemisphere. Everything north of the equator is the northern hemisphere. Everything south of the equator is the southern hemisphere. And in the corner, the bottom left-hand corner of the screen, I have a little compass. So it shows up is north, south is down, west goes to the left, and east goes to the right. So for example, what is the latitude and longitude of point M on the grid below? So the way that you do this is you have to write latitude first and then longitude. And also remember to write north, south, east, and west. So the way that you do this, you look, here's point M, and you go across and see what line is point M on. And it's on the 2 degrees north line. And then you look what vertical line it's on. So you go down and it's 1 degree west. So the answer here would be 2 degrees north, 1 degree west. Okay, so again, here are the answers. 2 degrees north would be your latitude. 1 degree west is your longitude. Then we could talk about how to look at the distances on a map. So you could look at distance using a ratio scale. That's when a map scale is written as a ratio. So for example, you could have 1 to 24,000. That means that 1 of any type of measurement, centimeters, inches, feet, even like a length of a candy bar on the map. So 1 of that measurement is equal to 24,000 times that same measurement on the land represented in the map. So for example, 1 inch on a map would then be 24,000 inches on that map, if the map scale is listed as 1 to 24,000. Actually, that's 1 inch on a map is 24,000 inches on land. Okay, so that's actually, that should say land, not map. Now you also have this PowerPoint. I downloaded it, I uploaded it to Blackboard. So you actually have this. So you can just go in there and fix that to say land instead of map. So also you can have a bar scale. That's a line on a map that shows a specific measurement that is equal to a particular distance on a map. For example, this line here represents 1 mile on a map. Or you could write a scale like 1 centimeter on the map equals a kilometer in real life. So this is how you would see a scale listed on the bottom of a map, where you have a line and it says, okay, like this is between this line and this line is 1 kilometer, and then that's 2 kilometers. Here's miles, and then the bottom one is feet. But note, the 0 is not on the end. It's not like a ruler. So they put the 0 somewhere in the middle, or off to the side in the kilometers case, off to the side on the feet. And then to the left of the 0, the distance is broken down into smaller pieces, smaller increments. And that's going to help you do more accurate measurements when you have a distance that's less than a kilometer, or less than, in this case, less than 1,000 feet, or less than a mile. Okay, so keep in mind that you have to always make sure you know where the 0 is. So this is a quick video showing how to measure using the bar scale on a map. So what I want you to do now is practice. Use the following scales to draw straight lines on a piece of paper. Draw 1 line for each of the following distances. So however you're looking at the presentation right now, whether it's on your computer or a tablet or a phone, I want you to take a piece of paper and draw a line that's 12,000 feet long and then 3 miles long, according to the scales that are on this map. So do that right now, okay? Okay, so again, I drew my 3 mile line and my 12,000 line. So then we're going to talk about topographic maps. Topographic maps are also called contour maps. They are maps that show the different elevations of different parts of the land. So this is a little piece of a topographic map. This is a section of the Paterson, New Jersey map. And when you zoom in, you see that there's this hill, there's hills here. Oops. There's hills here, and then there's numbers written on different parts of the hills. So the lines, these brown lines represent different elevations. Each line on this particular map is equal to 10 feet. So like the line that says 650 is actually 650 feet. The 700 line is 750 feet. And that was labeled at the bottom of the map, where it says the word contour interval, and we'll get into that in a few minutes. So contour lines are drawn to connect points of equal elevations on a map. So again, back to that 750 line. Anywhere on that 750 line, anywhere on that 700 line is at an elevation of 700 feet. That's why it's on the line. So it connects all the points of the same elevation. And then other features of land are shown on a topographic map, like bodies of water, parks, and roads. So the top diagram here shows you what the land looks like from the side view. Kind of like a 3D image of land. The bottom picture shows you a topographic map of the same landscape. So the bottom is a topographic map. So sea level is what we call the elevation where the sea meets the land, and that's going to be at the coastline. Sea level always has an elevation of 0. And then land is relative to sea level. So the elevation of land is going to be above sea level. So 10 feet above sea level, for example. So what happens when points on the land are not on a contour line? We can interpret the elevation of land that's in between contour lines the same way that you would count between numbers on a number line. So if this is a 10-foot contour line and that's a 20-foot contour line, but let's say you have something that's at point A that you want to find out the elevation. So you want to find out that elevation of point A. What do you think it might be? Again, you're using it like a number line. Now, if you don't remember what a number line is, it's like if this is 10 and that's 20, so then you figure out it would be like 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's what a number line is. Okay, so what might an elevation for point A be? You could write it in the chat. Also, when you write things in the chat, it lets me know that you're here. Okay, yeah, so about 15 feet. Okay, that's fine. So you interpreted because point A is kind of in the middle between 10 and 20, right? So you would say A is about 15 feet. So there were other rules of contour lines. For example, hills are going to be shown as concentric circles with the inner circles representing the higher elevations. Note, sometimes only a section of a hill is shown on a map. In that case, it would look like this, where it's like only like a quarter of the hill. But you still have circles. You can tell like it's just a section of the circles, but they kind of do still look like concentric circles. A ridge is an elongated narrow hill, so that would be oval, but it would be like still concentric. Concentric just means one circle and then there's a smaller circle inside and then a smaller circle inside that, etc. Then we have depressions, which are basically just holes in the ground. Depressions are represented by concentric circles with hatcher lines drawn into the hole to represent that the land slopes downward into the ground. So these lines are called hatcher lines. So anytime you see that, it tells you that the land is going downward into a hole. That's called a depression. Then we have something called a benchmark. A benchmark is a point on a map where the exact elevation is given. Benchmarks are marked either by a triangle, an X, or sometimes the letter BM. So in this case, exactly at that letter X is 32 feet. Then we have regional relief. Regional relief is the range of elevations represented by a map. So basically it's the highest elevation in an area minus the lowest elevation in that area. So for example, what is the regional relief of this hill? Yes, that is correct. So it would be 30 feet. So the regional relief of this hill is 30 feet. So we know that the hill is 30 feet tall. Some other rules of contour lines are that when contour lines are close together, it indicates that the land is steep because the elevation is changing a great amount over a short distance. So there's going to be a lot of contour lines smushed into a small distance. So here I have a side view of an example of a steep land area, and then the contour lines are very close together because you're going up in elevation pretty quickly. When contour lines are spread far apart, it indicates that the land is flat or gently sloping. So here's the side view of an example of gently sloping land, and then the contour lines are spread apart. Then we have a trick to determine the direction that rivers are flowing. So there are two ways. First of all, keep in mind that rivers always flow downhill. So the first option of how to determine the direction the river is flowing, in this case, the Apple River, which I already drew the arrow next to, but you could determine where the elevation is going downhill. So in this case, you have this contour line is labeled as 15 meters. This is 10 meters, and that's 5 meters. So the southwest direction, going the way the arrow is pointing, shows going from 15 to 5 meters, that's going downhill. But if these numbers were not shown here, and you only had the contour lines, you can actually determine the direction the river flows also using the shape of the contour lines. So when you follow the contour line, as it crosses the Apple River, or any river, it forms a V shape. And the V shape kind of looks like an arrow that's pointing opposite the direction of downhill. So in other words, the V shape points towards the uphill direction. Anytime a contour line crosses a river, it forms a V shape that points uphill. So rivers flow downhill, so it's going to be the opposite direction that the V is pointing. Now let's see how to determine the contour interval of a map. So there were two lines labeled with elevations, the 500 and the 600 meter lines. Oops. So here's the 600 and here's the 500. So we can determine how to count from 500 to 600 based on how many lines there are. We want to figure out what each line equals to. So what I mean by that is if this is 500, you could start counting, like let's say, usually contour interval is going to be either 10, 20, 50, 100. So if this is 500, we could pretend that it's a contour interval of 10. We can just try that out. So let's say this is 510. The next line would be 520, 540, 560, 580. Wait, that's not 10. I said count by 10. 500, 510, 520, 530, 540, 550. So notice how when I got to this black line that says 600, when I counted by tens, I only counted to 550. So what number would I have to count by in order to get to 600? 20. Okay, so 520, 540, 560, 580, 600. So that means each contour line is equal to 600, and in this case, it's meters. So that means that the contour interval is 20 meters. Okay, so the contour interval is 20 meters. So once you have the contour interval, you can label the contour lines with the elevations that they represent. So then what I did here is I went ahead and I labeled all the contour lines. Because sometimes I will ask a question that says just label the contour lines with their elevations. So that's how you do it. You have to figure out the contour interval and then you just label. But you have to figure out like what the uphill direction is. So you go, that says 600, that's 500. So you're gonna go up in number. So then we can, when you go to question 3 in the mapping lab packet, there are different questions like what is the contour interval, what is the elevation of each of the following points on the map, etc. So you can go and do that later. Let's see. And then latitude and longitude practice. This is also in the mapping lab packet, this question, where you're going to label 5 of the following cities. You don't have to do all of them, I mean, unless you want to, but you're gonna pick 5 of these cities and label them on the map. Now you could either print this page out, label, and then you would take a photo or scan your answer, or you can use the snipping tool, make a snapshot of this and then draw on that. There are different ways also, and then the next part, you have to determine the latitude and longitude of some of these points, well, all of these points. So we can do that later, but now I just want to get into field maps, and then I will give you the rest of the lab time to work on the packet. So a field map represents an area where there is a value at every location on the map. So field maps can show temperatures, elevations, concentrations of a chemical after a chemical spill, etc. In this map, this is a temperature map of the United States. The temperatures are shown in degrees Fahrenheit. So this is a field map because every single place in the United States has a temperature. Now, only the multiples of 10 are labeled with a number. So it says like 40, 50, 60, 80, 90, 70. But that's because you can't have a map just filled with like millions of numbers everywhere, because then you won't be able to see anything. So we just label, let's say by 10 or by 20 or something like that, so that you could see a clearer picture, okay? But then you would interpret the numbers in between. So if let's say this number here says 80 and that says 90, you could interpret maybe maybe there's like an 81 a little bit south of the 80, for example. So you would go through an interpretation. But that's what a field map is. It's any map where there's a value of something. So in this case, it's a temperature field map. So topographic maps are field maps of elevation because there's elevation everywhere on Earth. Whether it's above sea level or below sea level, there's an elevation everywhere. So isolines are lines that connect points of equal values on a map, on a field map specifically. So look at the map shown here. Lines were drawn to connect points of equal temperatures. And in this case, it went by tens. So all of the 40 lines were connected with a single line. All the 50 lines were connected, all the 50 points were connected. So they connected all the points with the same temperature. So when we're talking about elevation, we call it contour lines. But in this case, it's isolines. Isoline is like the generic term, and then the specific term for elevation is contour lines. So the following map is a field map with elevations labeled at different points of the land. This is question 6 in the map lab packet. So elevations are shown in meters. You're going to draw the following contour lines, 18, 20, and 22. Now, I've already drawn in the 18 line for you to show how to do it. Okay, and then there's a question about topographic profiles where you're going to draw the side view of the land. So in this case, this shows you the top view or the contour map of a hill. And then on the right, it shows you what the side view of that same piece of land looks like. And you have 2 different examples here of hills and what the land looks like from the side. Let me just see something. So the rest of the presentation just goes through how I drew a profile of this particular map. Okay, so it's a tutorial. And then I have this video here. So I'm going to stop the recording and I'm going to show you the video. Okay, so then at the end of the PowerPoint presentation, there is a set of slides that show you this map and a grid on the bottom, and then it shows you steps in how to draw a topographic profile. So I have all these steps here. So that corresponds with the very last page of the Mapping Lab packet, where I have this map where I already labeled the contour lines for you, and I have this grid. Okay, so as you can see, the Mapping Lab packet has a lot of diagrams that are quite large. So it makes it look like it's a large packet, but it's really just a lot of diagrams. Okay, and then the Mapping Lab outline that I gave you is pretty much similar to what we just went over in the PowerPoint. Okay, it's a lot of the same things, except for at the very end, we have something that says gradient. So for gradient, it is rise over run, or change in elevation over distance. So the way you would figure out the gradient is basically figuring out how steep is the land in an area. So here's point A and here's point B. And then the question is, what is the gradient between line A and line B, or point A and point B? So then it goes through the steps here. You do the change in elevation. You have to figure out what point B would be. So it's 10, 20, 30, 40. And then you get the difference between B and A. And then you would measure that line. The horizontal scale is 1 centimeter equals a kilometer. So you would actually take a ruler and measure between A and B. And then you would do the calculation. The other thing on here that we didn't go over in the presentation is calculating the maximum elevation at the top of the hill. So here is the side view of a hill. And this is in the Mapping Lab outline. So here's a hill, the side view, and then here's an overhead view of the same hill. So we can calculate the maximum elevation that that top of the hill could possibly be. So if there were one more contour line at the top of the hill, it would be 30, because here's 10, here's 20. If there were one more contour line, it would be 30. But there is no 30 line, so you just subtract 1. So what would the maximum elevation of this hill be? Write it in the chat box. Yes, that is correct, 29, right? So 10, 20, the next contour line would be 30 if there was another contour line. So then you take 30 and subtract 1. Okay, good. So now we're going to go to the Mapping Lab packet.